question 8. I don't know if maybe you found it fine. Question 8 in exercise 7F, which is about product rule. Okay? So if you're fine with this question, then just carry on. But otherwise, you can pay attention. So, I think it's not that hard. So what is the derivative you get from a quotient rule? What do you get for dy and dx? What we get?
A bracket 2x minus alpha.
Is that right? Yeah? Does that check out? Okay. That seems, yeah, that's about what I'd expect. It's, there's our degree 1 versus degree 2, because you differentiate, you'll lose a degree. Okay. So now, what do we have to do? Show that the tangents at the x-intercepts have opposite gradients and meet at a point M whose x-coordinate is the average of the x-intercepts. Okay, so I think this is a Cambridge thing, I don't know. They just really are keen on long sentences. And long sentences are a bad rule for journalism because they're hard to understand. So let's take this apart, shall we? This quadratic, what kind of a graph does it represent? It represents any kind of quadratic with roots at alpha and beta, right? And that A, all it does is it scales it up or down, okay? So therefore, what kind of situation am I getting? Alpha, beta. Okay, so now let's start to put together the question from the information from the question. The tangents at the x-intercepts. So here are my two x-intercepts. Let's put in the tangents. And you can see, because I've drawn it, like it's reasonably accurate, that you're getting at something like this. That's pretty close versus this. Okay, is that about right? Yeah. Show that the tangents at the x-intercept have opposite gradients. Okay, so if this was gradient 5, you'd be expecting gradient minus 5, which does look like it checks out. And meet at a point M, whose x-coordinate is the average of the x-intercepts. Okay, so this point M, right, we're expecting, I don't know what its y-coordinate will be, so I'll just call it y. But I'm expecting this part, which some textbooks, they use a really weird techie name. They call it an abscissa, which just means x-coordinate. They want it to be the average of these two, so alpha plus beta on 2. Okay, so that's what I'm expecting, yeah? So how do I work this out? Well, if I want to work out a point of intersection, I'm going to need to know the equations of these lines, right? So how's that going to work? Well, we've been looking at tangents and normals before. Let's do them one at a time. If I want the tangent to the curve at x equals alpha, okay? Another way of saying that is it's alpha, and I also know its y-coordinate as well. Because it's the intercept, it's alpha 0, right? Okay, I'm getting both those pieces of information because I'm going to need to know the point, and I'm going to need to know its gradient as well. And then I can plug it into point gradient form. Okay? So, at this point, at alpha 0, the gradient will be, okay, so I'm just going to evaluate dy and dx at such a point, okay, which doesn't turn out to be that hard because of the numbers. You get 2 alpha minus beta. So here you've just got alpha minus beta. So now I can pop it into point gradient form. So the equation of the tangent will be y minus y1, which is just 0, is equal to m, there's my gradient, outside of x minus x1, which is alpha. Okay, so I'll just get rid of that 0. Okay, now, that's fine, but what was I actually interested in? I'm going to have to find, number 1, the gradient of this line, and number 2, where it intersects with the other one. So before I go any further, well actually I already know the gradient. There it is. Okay, so tick. Now let's have a think about the other line. Okay, once I have the equation of the other line, then I can work out where they intersect. Okay, so I want to find the tangent at, not alpha 0, but beta 0, right? And because it's so similar, a lot of it's going to pan out exactly the same. The gradient is going to be alpha times 2 beta minus alpha minus beta. So there's my new gradient. So if you like, I can call this gradient 1 and gradient 2. And you can see one's the opposite of the other. That's what they mean by they have opposite gradients. Okay, so I can say here m1 is equal to negative m2. So that's what they mean by opposite gradients. Okay. All right, next step, let's work out the equation. Okay, so it's going to be y equals, and you can see because it's so similar, again I'm going to get minus 0 over there. So I've got a beta minus alpha x minus beta. Okay, so now I'm after a point of intersection. So, if I'm after a point of intersection, and I'm only interested actually in the x value, right? I'm going to substitute my y's, then my equation will just be an x, okay? So what do I got? I've got the right-hand side here, x minus alpha, and I've got the right-hand side here, x minus beta. Now, don't forget, by the way, we said that this was m1, and this was m2, and they're just negative of each other, right? So I can just put, let's see here, x minus alpha here, right? And this will just be minus x minus beta. Just divide it all the way through, okay? So now, I just clean up here. I've got minus x plus beta, x minus alpha, and I want x to be the subject, so 2x over there, alpha plus beta over here, and there's the result we're expecting, okay? So, what were the pieces? Number one, we had to get a picture of what it looked like so that we could work out what's our approach. Then you do have to find these two equations, and there's no shortcut around that. But thankfully, the algebra works out quite neatly because how similar these equations are. And then you have to work out this part here, the opposite gradients business.